Hi, my name is Adolfo Campos, and today I will explain the experiment of the Venturi tube. So first of all, we need to understand what is a Venturi tube. It will be this contraption right here, just this tube on top. Basically, it's a tube that starts with a big area, and then it becomes small, and then becomes big again. So there is a small area in the center and two big areas on the extremes. So, well, if we try to apply the formulas we have seen for pressure and area and velocity to the Venturi tube, specifically we're going to take this point 1, which will be in this area right here, and this point 2, which will be this smaller area right here. So here is the formula for the change, well, for what stays constant basically. So the pressure plus the density times the gravitational constant times the difference in height plus half the density times the velocity squared. All of these are of the fluid, specifically the radial fluid that is flowing through a tube, will stay the same in another point, as you can see here. So therefore, the values of all of these in this point 1 and this point 2 are the same. But we are using a Venturi tube, we can actually eliminate some of these terms. First of all, density, gravity, and height are the same on both points. This is because, well, density and gravity are constants, but they are not at different heights, so therefore these two can be cancelled. And we get the following formula. Then we can simply define change of pressure that as the pressure of point 1 minus the pressure of point 2, and therefore we can pass it to the other side, like this. As well as pass all of these terms to this side. So now we have this formula right here. But what if we use the formula for the constant that is the area times the velocity? So as you may remember, when we have a gas fluid in a tube, it is incompressible. So therefore, the same amount of volume has to pass at the same time. So therefore, we can say that the given area at the point times the velocity of the fluid at that point will stay the same. Well, its multiplication will stay the same. And we call this value the rate flow, which will be this right here. So therefore, we can simply use this part right here, A1 times plus D1, and the rate flow, and just isolate velocity. So we get this formula. You see, we replace velocity with this formula right here. But there's something curious right here. Well, both are multiplied by half, which is obviously a constant, and the density of the fluid, which is also a constant. The only well, velocity at point 2, if we always are going to use point 2 and we just want to calculate any other area, not just point 1 right here, for example, an area right here or an area right here, etc., then we can say all of these three are constant. And for the second part, well, both this and this are constant as previously. And as you remember, the rate flow is also constant in any point. So therefore, the only variable right here, if we want to calculate another point using point 2 as reference for the change of pressure, is just this area 1 right here. So therefore, we can simplify the formula by just taking into account these constants as constant 1 and constant 2, or C1 and C2. So basically, in a Venturi tube, the change of pressure by using a point of reference, specifically point 2, which will be the smaller portion of the Venturi tube, will always be this value right here, which is just two constants. So therefore, in this experiment, we're going to try to prove this relationship, that the only thing that change pressure depends on is the area of the point we're going to try to measure against in this case, point 2. Okay, so here this quick experiment. What we're going to do is we have a Venturi tube, and as you can see here, on point 1 will be in the previous one what was point 2, and here we have some other points along this Venturi tube, right here, right here, right here. This will be point 2, 3, 4, And what we're basically going to try to do is get the areas for all of these 4 points and the change of pressure against point 1 in all of these in order to prove this formula. So the change of pressure is equal to constant 1 divided minus constant 1 divided by area 1 squared plus constant 2. So here is a mock-up of the experiment. As you can see right here, we have a big fan sustained by a base connected directly to this venturi tube. Now, as we're going to use air and not a better ideal fluid like water, we're going to have to take it. We only can take the points after this point right here, as all the previous points will be affected by friction from this radical change. So therefore, we're going to use only these points. So basically, here it is. What we're going to do is connect these parts right here. Well, actually don't connect it at all. So therefore, on this point, the pressure is ambient pressure in order to make the calculations easier. And instead of using these tool right here, which will be a manual way to measure the pressure and velocity, we're going to use an automatic one with the Pasco interface. So basically, we're going to connect a Pasco to this venturi tube on the correct terminals, measure the pressure in all of these points. And as we're using the Pasco venturi tube, we can already know the areas as they are stated on the manual. So therefore, we only need to measure the pressure. So it will be connected, and pressure will be measured. And when it gets to this area right here, we're going to measure it, wait for it to stabilize, and then measure another one. So therefore, we'll get with 4 points with areas and pressures, which are these ones right here. So as you can see, the first area, which is the smallest cross section, well, it's the smallest area, obviously. The areas get bigger as you go along the venturi tube, and the pressure starts increasing. Well, here they are negative, therefore, if they get smaller, they're increasing. So therefore, we're going to just we'll get in y-axis this change of pressure right here, and on the x-axis this area right here. We're also going to calculate both C1 and C2 using the relationship, but the important thing is that the graph follows a very close relationship to this one right here, on where y will be the change of pressure, x will be the area, and so therefore the relation will be roughly like y equals constant, let's call it a, divided by x squared plus another constant, let's call it b. So therefore we're going to compare the results to this formula right here, graph them, and see if they fit. So as you can see here, from the graph right here, you can see they fit. They actually fit. Here is the calculation for the constants. As you can see, they are quite equal. It's because we use square centimeters and square meters. The units are not really important. That wasn't the point of the experiment. The point was to see these uncertainties and see how much would deviate from this graph right here. As you can see here, for constant 1, it's around an eighth of what it is, the actual value. So therefore, it is really close. It's just an eighth in difference. Sadly, for the second constant, it's about double it. But as you can see, it's much smaller than constant 1. So even this uncertainty doesn't change it at all. So therefore, these uncertainties are small enough to say with confidence that the venturi tube proves that this formula is correct. The derivation was correct, and the change of pressure on the venturi tube only depends on the area of the point you're measuring. The other values are just constants. Thank you for watching.